Hello, everyone. My name is Corey Baker. I'm a PhD candidate at in the Wireless and Mobile Systems Lab, and I work with Dr. McNair. And today, she wanted me to present to you all the research that I've been working on, talking about mobile ad hoc social networks. So I'll be presenting you message delivery for evolving community structures in mobile ad hoc social networks. So some of the things I'll be going over today with you all is I'll give you a background. I know you guys have been doing mostly centralized infrastructures. You're starting to go into ad hoc social networks, kind of Bluetooth direct connection networks. So I'll give you an overview of centralized networks. Then I'll go into delay tolerant networks, which can be used with ad hoc social networks. And then I'll go into my current research, which is low energy socially cognizant routing, and give you some information on how that works, and then tell you about the simulation results that I've currently come up with, along with an actual application that's using the implementation of the protocol. So let's imagine that we're all at the football stadium. How many of you all have been to a football game here at UF? You haven't been to one yet? You've been to? All right, so you guys have been to them. So imagine that we're at the football game and that these dots on the screen are different people at the game. And they all have Bluetooth capability. Now, let's imagine that we didn't really have a good season last year, but let's imagine we had a good season. We're playing against Florida State. We were losing the whole game, and with 30 seconds left, an event happened. We're going to go through that event. So first, at that event, there's 4 people that we're going to care about for this example. It's Alice, Carol, David, and Eric. So there, we're mainly concerned with Alice. When this event happens with 30 seconds left, we basically calls Florida State.
I'm sorry, I think your phone's interfering with the microphone. Can you get them maybe farther apart if you need to use your phone? Maybe move the transmitter for that farther around the backside.
Okay.
Sorry about that.
No problem. Does it sound? Do you know if it sounds better or now or?
It's good now.
Okay. What about now? 1, 2, 3. Okay. Okay. So let's imagine that we Florida end up causing Florida State to fumble. And so Alice texts a message and she's saying, hey, we just recovered a fumble. We got to the 1-yard line. Right. So when she wants to send that message, say she wants to tweet, put it on Facebook, and tell her friends about what's going on at the game. So she tries to do that, and she tries to post a message, say to Facebook or Twitter, and what happens is, you guys know if you've been to a football game, you try to post that message and it's blocked. It says you have a network connection, but there's so many people around, there's congestion in the area, you can't post, and there's so many people around you can't even take advantage of them. Well, what would happen if we could take advantage of those people and basically post Alice's message throughout the network and disseminate those to the people who care about the message? That's essentially what I'm trying to accomplish with my research, and what you can do with mobile ad hoc social networks and delay tolerant networking. So first, let's go over centralized infrastructures, which we all know well. This is the typical case of where we had tried to post a message, and currently over 3 billion people in the world have internet availability like this. So when Alice tried to send her message, she put it on the server. She connected to that server, posted a message. When Bob attempts to receive that message, connects to the server, pulls down the message. We know that today is the cloud, right? And this is what a lot of people that have internet access use. Well, what happens in the case that we mentioned, or what about people? What about the 60% of the world who don't have internet access? Or what about the cases that we just mentioned in our example? Well, what happened is Alice attempts to post a message. When she tries to post that message, it's blocked for some reason, could be congestion or something else. And then we're not able to receive that message. Bob is not able to see that message because it never got posted, or any other messages to get delivered. This goes into many issues. One, congestion that I mentioned earlier, central port and failure, IP blacklisting, and the kill switch. I'm going to go into a little bit of details about the kill switch. Does anybody knows what the kill switch is? Okay, so the kill switch is basically what happened in 2012. In 2012, in Egypt, or in the Arab Springs, the government essentially cut off the internet to anybody that was using it. The reason why they cut off the internet is because people were staging protests. They were using Twitter. So they were saying, meet in this location, we're going to protest about this here. And the government didn't like that. They were trying to stop that type of communication. So what they did is they essentially hit a button by contacting all the internet service providers and said block Twitter, block the internet for anybody who wants to use it. That's kind of how the government actually tries to manage connections in China or to Facebook, but of course there's ways around it. But that's what happened in Egypt, and this can be done almost anytime, anywhere. So that's the kill switch problem. The other issue that arose more recently is in 2014 in Hong Kong. You guys know about this, what happened with Fire Chat? So basically the protesters, the internet connections out there weren't as strong where they had all the people at, and people were trying to stage protests at this festival. So what they did is they used the app Fire Chat. Do you all know what Fire Chat is? Fire Chat is an application. It kind of brings back the chat room aspect of communicating. So people jump in the chat room and they're able to talk about various topics. The one difference with Fire Chat is Fire Chat also enables you to do this without having an internet connection. So if you had the app installed on your phone, other people around you using Fire Chat, you can use Bluetooth or Wi-Fi to establish connections with the people around you, and you communicate. So they staged protests in Hong Kong, I believe it was towards the end of 2014, and they all communicated using Fire Chat. Now this is big. We all know security and privacy is one thing that everybody's looking for nowadays. And so when you look at this type of connections, I think in Hong Kong they had over 100,000 users download this app within 24 hours, which is enormous, right? So there's definitely use cases, and there's potential issues to try to get around centralized infrastructures. So delay tolerant networking. Delay tolerant networking is basically the opposite of centralized infrastructures. It's a decentralized infrastructure, and it's highly dependent on nodes. One difference is delay tolerant networks is not necessarily establishing a new radio for communication, but it uses current technology that's available, such as Bluetooth, LTE, Wi-Fi, and runs on top of those technologies. This allows you to deliver messages in the case when there's no infrastructure. In the case where I mentioned at the football game, or in more serious cases such as disaster relief type scenarios, military applications, in underdeveloped countries, say for instance how I mentioned in Hong Kong, well, not underdeveloped, but necessarily if there's no infrastructure in those areas, you can deliver messages in those types of areas. Now, some of the trade-offs of using delay tolerant networking, as the name implies, you're going to receive messages with a delay. Sometimes you can't predict that delay. Sometimes you can. It's highly dependent on the node's mobility. If a node, say a node is a person, if that person has a sick day and they're not going on the same path that they typically, then you might not be able to get the message delivered in the expected time. So epidemic routing, you guys are all familiar with epidemic routing, right? Or flooding. So epidemic routing is the flooding protocol. What I want to do is I want to give you all an example of how epidemic routing will work in a delay tolerant networking case. So then we can kind of see and compare it amongst other protocols to the protocol that I developed. So in epidemic routing, we're going to use the same example that we used at the football game. And we said it was 30 seconds left. Alice had a message to say saying that UF just made Florida State fumble, right? So when we in this case, Alice is in Bluetooth range of say Eric, Carol, and David. So when she's in Bluetooth range of these three people, she's basically able to communicate with them. So she posts her message. Say it was like a Twitter message. So when she posts that message, basically everybody that's there that's in communication range is able to receive that message. So here we use R in yellow for receive. F stands for forward. So F means they're forwarded a message. If you guys remember in epidemic routing, you basically push the message to anybody that's around, and then they're going to push it to anybody who's around them, right? So you basically force the message out. So say that's at 30 seconds. Say when we got this touchdown, we got to the 1 yard line, we called 2 timeouts. So let's give a 5-minute interval to after this time. Let me mention one more thing. Is you see that during this case, Bob was out of range and didn't receive the message, right? Because let's say he was in the restroom when all this happened. So now, 5 minutes later, the people who received the message got the message and they're designated forwarders. What happens now is say David went to buy cotton candy. So he went around and he ends up coming into Bluetooth range, or it could be Wi-Fi either. Also any wireless range that the protocol is using with Bob. So when it comes in range with Bob, everybody's still in range of Alice. Now this new message gets propagated to Bob. Bob receives the message and now he's designated a forwarder, right? So that's a typical case of how epidemic routing can work in the case of trying to push out one message. So next, let's go into the protocol that I'm working on, low energy socially cognizant routing, and see some of the details of that. So LESC is low energy socially cognizant routing, or LESC, is a message delivery protocol that's set up like Twitter. And when I say Twitter as opposed to Facebook, Twitter doesn't force a two-way communication between users. Basically, you can subscribe to one person, they might not subscribe to you. In Facebook, you have the friend aspect where it basically establishes automatically a two-way communication when you become a friend. Even though with the new Facebook, you can kind of do some things by unsubscribing, but still, typical Facebook, you establish a two-way friend communication. Unless you can have a two-way communication, but it's not forced upon the user. There's no network infrastructure needed to work. It's a delay tolerant networking protocol, and it's based off of ad-hoc connections through users and takes advantage of, say, Bluetooth or LTE or any other wireless that's available. And it can utilize centralized infrastructure. Say, for instance, in the case I mentioned of the football game, there's no internet available for a short time. So say you resort to this protocol and then can go back to using typical centralized methods if there's internet available on a device. How does it do this? Well, we propagate messages by measuring and trying to forecast two main items. These two main items are interest group co-location. So interest group co-location is basically what we're doing right now. We're co-located, we're around each other. So say, for instance, for this class, we'll probably be around each other for at least 50 minutes, an hour if you guys want to stay later and hear me talk, right? So we're co-located around each other. If you're around people who are interested in the message, then it's a good chance, or if you tend to be around people who are interested in the message, you're probably a good passer of the message for that particular social group, right? And the other item that we look at is diversity nomadicity. Basically, how many different nodes do you encounter, do you tend to encounter in a network if you're a nomad? If you go around and you frequent and you don't stay in one place a lot, you are a good passer of the message too. We want to know that. That means you go around different communities a lot and you can be a good passer of the message. So we take advantage of that by measuring it, and then we try to forecast, and you can forecast using Kalman filters. There's other filters available to basically try to project out, build a model, and see if you're a good passer of this message and can you help us deliver messages. Of course, with LESC, there's vulnerabilities, as with almost any protocol, or especially a DTN. Delay tolerant networks are typically vulnerable to the underlying vulnerabilities in that wireless technology, meaning that if there's a security flaw there, it could be a potential issue with the protocol. I'm not necessarily a security person, but you can do security things at the application layer of your protocol to basically ensure that it's more secure than maybe the underlying technology. But typically, if you don't do that at the application layer, you're open to those vulnerabilities. So one thing about forecasting, I wasn't going to go into the details, but if you have an equation to measure, which I didn't show the equation for the two items that I mentioned, but if you measure, if you're able to measure an item and say you can use something like Kalman filters to assume it, if you assume that that item is linear, and you can use that to project out. So basically, you have a current time, you measure what's going on, and you say, give me a prediction that say 10 minutes, an hour ahead. What can you do with this this item? And if your system is nonlinear, you can use you can use nonlinear filters for that. You can also use Kalman filters, say for instance, if you don't know what the model of the system looks like, and you can build that model using something like a Kalman filter. So how does LESC differ from other delay tolerant protocols? It's not the first delay tolerant protocol out there. There's many out there, especially now, especially if you remember the issues that I mentioned earlier. There's so many issues out there, especially with disaster relief, what happened with the security privacy thing of governments trying to monitor. There's a lot of DTN protocols that are becoming available. So some of the related works I noted on here, one of the protocols is called SocialCast. So SocialCast attempts to forecast nodes, social interactions of nodes using Kalman filters and other filters, and it projects messages, it sends messages out. But one of the things that kind of differs is that this protocol was designed in simulations, and during simulation it has like a 250-meter propagation range. The car is actually, SocialCast was built from cars, so they're the same people that worked on those protocols. It's very similar to SocialCast, except that it uses a unicast approach as opposed to using a multicast approach of sending out a lot of messages. CSI is a protocol that was developed by Hisu, and then also, I'm not sure if you guys are all familiar with Dr. Helmy here in the CIC department, but they developed this protocol, and it looks at mobility profiles, and based off those profiles, try to deliver messages targeted to that profile. They also, in order to deliver messages, it kind of uses a fixed infrastructure of hoping that there's beacons around. So if you're in a place of no infrastructure, you establish some type of infrastructure by installing beacons, which can be expensive, can be taxing, and also adds additional things to the requirements of your network. With LESC, we developed LESC to take into the constraints of current wireless technologies. So a lot of you see those communication ranges up there from 200 to 250 meters. Bluetooth typically works realistically between 10 to 30 meters. If you look at it on documentation, it's going to say 100 meters, sometimes probably 150 meters, but realistically it works up to about 10, 30 meters when using it in places like a room or so on. And so we try to take in constraints of the current wireless technology. Also, a lot of the protocols assume that you can send large subscription lists, right? You can just advertise a lot of information. It's a pretty good assumption, but when you assume that you can just pass messages to whoever, or everybody can see who you want to pass messages for, it's kind of unrealistic in an actual realistic case. Less we take into account, we only pass information that's needed to users, and that users are actually interested in. And we're able to communicate with no beacons or no infrastructure. So some of the things I mentioned on here, one thing is that I want to mention is that LESC is able to infer locations by basically co-location and you being a nomad, right? We don't need to actually log your GPS location and go based off that information, know exactly where you're at. But our protocol knows who you're around and who you've been around. So from there, you can kind of infer location, which is, as I mentioned, less infrastructure than is needed by many of the other protocols. So let me go into the same case. We're going to go through the same example of how LESC would work in delivering messages for Alice in the football case. So Alice, at this, before I start actually, let me mention that Alice, this utility value that's under Alice is a little bit different than the previous slide. This utility value could say be anywhere between 0 and 1, with 1 meaning 100% and 0 being 0%. The closer that you are to 1, that means that you're a better indicator. We forecasted that you're a better projector to deliver our messages. All right, so we okay with that? So 0, you're not, the closer you are to 0, you're not a good passer of the message. So if Alice is 0.5, Alice is said to be 50% as good at delivering her own messages. Because in our case, in our examples, I've only talked about Alice's message, right? So Alice, we're going to use this number because it's going to make more sense right after we go forward. So Alice is 50% for her own messages. In the same case, 30 seconds happen. We made Florida State fumble. Alice has posted a message, hey, we just forced them to fumble. I think we're going to win the game, right? So when she posts that message, now you see that Eric and Carol are in red. They're in red because their numbers are less than Alice's number. So basically, they wouldn't be as good a forwarder of Alice's message. David, on the other hand, actually is at 0.6 and is in green. So since David is in green, David is a better passer. He's basically around, he's projected to be around a larger amount of Alice's community than she is, right? So when we pass this message, now this looks slightly different from the epidemic routing protocol. When you see here is that Alice designated Eric and Carol received the message, but they don't have an F, right? They're not designated forwarders. So basically, we won't use them to forward messages in the network because we're essentially projecting that they're not going to be around a lot of people that are interested in the message. When you look at the case of David, it has the R and the F. David received the message because they're interested in it, and they're also designated a forwarder. So when we look at the case with those two timeouts happened. It was 5 minutes later, right? So we're at the next time. We're still in the same case where people received the messages. And then now David moved. He went to go get cotton candy, moved in range of Bob. And Bob actually has a higher utility value than David. So now since we're in range, we can pass that message to Bob because Bob is interested in the message. But you see that the F actually moved from David to Bob. This shows one thing in the protocol too. Other people can be designators, can designate passers of the message. So say if you're a better passer than me, even though I got it from somebody else, I'm going to ask you to deliver the message because you might be around more people that are interested in the message. Is there any questions so far?
Does this imply that there is only one passer at any point of time?
No, it doesn't. There could be many passers, and I'm going to show that in the simulation results. What I try to do is I try to keep the example as small as possible, and then the simulations you're going to see about how it happens in the larger case. But there could definitely be more message passers than this one, because in the real, as you're alluding to, in the real social network, there's going to be tons of messages created. There's going to be tons of people who are interested in the message. So this is just for that one message. I'm sorry, can you repeat your question?
How are you deciding the utility value? Like on what basis?
Oh, so you asked how am I deciding on a utility value?
Yeah, like how is scan having 0.1 and epic is having 0.4?
So I didn't show the equations up here, but those are depending on the two items I mentioned before, the interest group collocation and the diversity and nomodicity. So between that, I measure those and then I do a forecasting technique. And I'm going to show you like the weights of which one I choose to care about more. But between those, I basically come up with a number. I have an equation that generates. And I didn't show the equation. I didn't show any of the equations because all that stuff, like we're doing patent stuff right now, so we don't have the equations out. But based off that equation, we say that you're 0.8 or you're 0.1, and then we say utility. Is there any other questions? All right, so next, we're going to go into the simulation. So how we design the simulator, because that's very important. How we set it up, and then some of the results that we've gotten with using the protocol compared to, say, other protocols. I'm going pretty fast. Okay, so we designed a simulator in MATLAB. For the simulator, we're able to emulate multiple nodes with wireless capabilities. So the wireless capabilities that we use for our simulations was actually Bluetooth Smart. Basically taking in the restrictions and the capabilities of Bluetooth Smart, and then also the transmission range. So by that is, as I mentioned, the 30-meter propagation range. So when you look at it from a simulation standpoint compared to the other protocols that I mentioned, we're simulating 30-meter propagation range compared to 200 and 250-meter propagation range. We're able to simulate things at close to the MAC layer. So we're able to simulate unsuccessful packet transmissions. And so we take into account, we're not just assuming that every message got disseminated whenever a node comes in contact. And that's very important in the case we're doing delay tolerant networks because, as you can imagine, we're dependent on node movement. And we're basically dependent on people movement. We can come in contact and I can be running very fast, and the next person that comes in contact with you can be going slow. And so if you just assume that since we came in contact, a message got disseminated, it might give you erroneous results. And then, I'm sorry, I forgot to mention one thing. So also, our simulator actually plugs into Google Maps. So with it plugging into Google Maps, we're able to place nodes on any basically area that Google Maps is able to give us. So whether it's another country, another city, UF, which I'll show you in a second, we can place nodes in that location and make them move over paths that Google Maps gives us. So we're not just doing random movements around a particular area. So, I'm sorry, going too fast. So here's the simulator setup. As you see here that this should look familiar to you all. This map area is UF Wright's North Lawn before all the construction. So before all the construction, there used to be tons of people over there, especially around lunchtime, 1 o'clock p.m. These dots here are nodes. So there's actually, we simulated 100 people. There's about 200 dots here because there's 2 endpoints. So we randomly place a node on there and say you have 2 endpoints and you have to move over your path. And if their path is short or shorter, they'll traverse that same path the whole during the simulation. So this map space here is 500 meters by 500 meters. We had 100 nodes in the network, and we had them walk around 1.5 meters per second, meaning that's around typical walking speed for each node. You can do stuff by having some nodes go faster, saying they're riding a bike, but we had every node say walking speed in this case. And they all had the transmission range, as I mentioned earlier, of 30 meters. Now, we also had a publishing interval of 60 seconds, meaning that we said that each node can create a new message within 60 seconds. Within the max they can do is in a minute, and the max you can create in a minute is right under that. It's 2 messages. So we attempt to say there's some fast typers out there nowadays, but we attempted to say if somebody's a tweeter, they can only at max create 2 tweets per minute if they're tweeting, right? And with that publication, we only let nodes create messages the first hour of the simulation. And the reason why we did that is because, as you guys know, people keep creating messages. That doesn't give us, we attempted to steady state the system by looking at, you can only create the first hour, then stop creating new messages. You can send messages that you have, but try to steady state the system and see how long it takes to deliver all the messages within the network. So now, looking at the protocols, this kind of goes into what you were asking me about what we looked at for LESC. So say, I didn't give the equations, but say for instance for the typical protocol for LESC, the second column that you see here on the bottom graph, what this says is that for co-location, the one area that I tell you we looked at, we depend on 60%. And we depended on you being a nomad by 40%. So that was our initial assumption. We basically assumed that if you tend to be co-located around a person, that is more important than being a nomad. That was an assumption that we made, right? So that's how we ran the regular version of the protocol. Then we looked at what happens if you are a nomad. So if we depend on you being a nomad 100%, how would you deliver messages, right? Because we wanted to see, we made an assumption, we don't know if that assumption is correct. So how would it if you're actually a nomad? Then we looked at the opposite. What happens if we just fully depend 100% on intergroup co-location, and we wanted to see how that delivered? And then we compared that to individual delivery, basically a node's capability to deliver its own message without using a routing protocol. Because of course, if nodes are able to deliver all their own messages, then what's the need for a routing protocol? So we want to see how we perform against that. And then we also performed against the flooding protocol or epidemic routing. So the hysteresis threshold is not too important right now. That was a threshold that's set to help out with calculating utility number to see if we want so messages don't go back and forth. The max nodes of messages to pass. So basically, if a node does ask somebody to pass messages, they're only able to designate 50% of their subscribers using LESC, right? So we want to cut out message passing. So we say that if I only have 50 subscribers, I'm only going to ask 25 people to pass messages for me. That's essentially what we're saying. Next, and then what you'll see for epidemic routing, there's only 100 nodes in the system. So of course, this number 99 is really infinity for that one, because you can just designate as many passwords as you want. And then hops to live is really how many people can the messages go through? How many hops will the message live? And that basically tries to get the messages out of the system, so we don't attempt to do something like flooding protocol and have a lot of unneeded messages out there. And then the max copies generated. So when I designate you a passer of the message, you can only pass out 50. There's only 50, and the reason for that, we really just cut the amount of subscribers in half. There's 100 nodes period, so we said 50 would be a good number for that. And then this kind of goes into some of the details of Bluetooth, and I think you guys went through Bluetooth already, right? Regular Bluetooth. So we attempted to look at Bluetooth Smart, which is a lot more low powered. Does some things differently. So it works in the same modulation band. Frequency band is Bluetooth at 2.45 or something like that gigahertz. It works in the same frequency band, but it does things a little bit differently. So it has an advertising mechanism in there, and with the advertising mechanism, it works over 3 channels. in an advertisement packet, you can put what we designate is our buffer size. We said we can advertise 4 essentially people in each advertisement packet. So if there's 3 channels, we assume that we can only pass for 12, meaning myself, if we were talking about me as a node, myself and 11 other people, right? For if you're interested in these messages. That works a little bit different than standard Bluetooth, just because the advertising mechanism is not there in Bluetooth. And also the amount of channels Bluetooth uses is like, I think 80 or 79 or something like that. And Bluetooth LE has a 40. So they use the same space, but they use it differently. So let's go into the results. So the results here, first, this green line, this is where I told you where messages stop creating new messages. So I want you guys to see that point. So you see that it marks an important point during the simulation. No new messages are being created after this green line point. And we're going to look at through all the cases that I told you for message delivery. So first, let's look at LESC. LESC is the 60-40 case that I told you, right? 60% interest group co-location, 40, depending on 60% interest group co-location, and 40% diversity and nomodicity, right? So depending on that, by the end of the simulation, we got pretty close to 100%. This is in minutes, but this is essentially 3 hours, right? If you see when messages stop being created, we're around, it looks like around 40%, right? So that's how LESC performed for average message delivery. Now, when you look at diversity nomodicity, it performed almost the same. In some areas it performed, you can kind of see it's a little bit under, but it performed essentially the same as the LESC protocol. And remember that LESC takes in part of how diversity nomodicity works. When you look at interest group co-location, this depending on interest group co-location, it performed, average message delivery was less. It wasn't a lot less, but it was less. By the end of the simulation, it looked like it got to 90%. Now, one thing to point out when we're going through the rest of the simulations is that, or the rest of the results, is that during simulation, each node basically started out dumb, essentially. And by dumb, I mean it knew who follows them, it knows who they follow, and it knows what path they're going to walk, but it doesn't know anything about what nodes it's going to encounter. Because remember, I told you the protocol basically looks at who you've been around. So at the beginning of the simulation, the nodes don't know who they're going to be around. So when you're looking at, depending on diversity, nomodicity, interest group co-location, the node doesn't know it's going to be around a lot of nodes. It doesn't know if I'm going to be around them. It only learns it when they see them. So you can see through the results that the protocol will start getting smarter as you move forward and start delivering messages or do different things. So when looking at epidemic routing, as you can see, and this kind of makes sense, the beginning of the simulation, epidemic routing actually has an average message delivery higher than all the other protocols. If you're flooding the network, if you're pushing it out to everybody, and the other protocol doesn't know the network yet, we're going to perform better, right? So epidemic starts off performing better, but you can assume that something happens in here where the network starts getting flooded, right? It's putting out so many messages, and basically the LESC protocol, all 3 versions of the LESC protocol start performing better than the epidemic routing. Now let's look at individual routing. How would nodes be able to deliver their own messages? So nodes will be able to deliver their own messages only by the end of the simulation up to 30%. So when you look at is routing needed in this case, routing, all types of routing basically helps significantly, because in our simulation, looking at the density of our network, how many people are in a certain space, only 30% of them would have received the messages that wanted to receive it by the end of the simulation, right? So that's looking at all messages. Those are all messages being propagated through the network, and I would call that a typical social networking case. Looking at we also want to look at one other thing, the first message. What happens is if an emergency message gets propagated through the network? We call that the first message. So if we assume that every node had an emergency message to send, that emergency message could be an Amber Alert. It could be something happened, somebody had a heart attack. It could be anything like that. How would that message propagate through the network? What's better to be used in that area, right? So when we look at average message delivery there, for all 3 of the LESC protocols, we see that diversity and nomodicity work better, right? So basically, the nodes, they still started out dumb in this case, but basically if you're a nomad, if you're encountering more nodes it says, hey, there's emergency going on. This is the first message of all the nodes. That delivered better than the 60/40 and it's depending on co-location, right? Looking at epidemic routing, you see something completely different. Epidemic routing worked way better. Basically, if you only need to flood for delivery anyway, if you want to flood the network with an emergency message, just looking at the first message, epidemic routing works fine, right? You're probably not going to flood the network with one message from every user. In this case, it'll be 100 messages, right? You see basically at the 60-minute mark, we got up to around 90% of the messages delivered by the time messages stopped being created, where the other protocols are more at 50%. So looking at this, you might want to use epidemic routing or take advantage of some of the techniques that epidemic routing puts out there. And when you look at individual routing, it's still around 30%. So in an emergency case, looking at that first message, epidemic routing for average message delivery worked significantly better. So now let's look at the delay. We talked about how many messages were delivered, but what was the delay of actually receiving these messages? So a little bit faster through these. If you look at all these, you see that the average delay for in all the messages case was by epidemic routing, right? The other protocols, actually the 60/40 case that we did, by the end of the simulation had the least amount of delay. Right, so basically when the nodes start learning each other, taking advantage of the two cases, the yellow and the green, of being a nomad and being around the interest group, we're actually able to be smarter and deliver messages with less delay. So now I want you guys to think about the delay being encompassed with the average message delivery. You got a lot less delay in this case with the LESC protocol, with more messages delivered so far, right? By the end of the simulation, on average, we had 13-minute less delay. For the first message, it works out differently here again too. I think it was the 80-minute mark, we're at 90% average message delivery for epidemic routing for the first message, right? Here, we had 13-minute average delay, where the other protocols were delivering where they're at around close to 25 minutes. So for epidemic routing, for that emergency message that went out, we delivered way more messages with a lot less delay. By the end of the simulation, there's a 30-minute difference between the delay of both, but you see that epidemic routing, essentially it delivered 90% of the messages, so the delay for the other messages didn't get affected as much. So looking at the number of messages put out in the network, let's see what happened there. So in the all messages case, the typical social networking case, we see that, of course, if we normalize this to epidemic routing, as you would assume, it's a flooding protocol, pushes out all messages, it pushed out the most messages. By the end of the simulation, we're only around 30% of the messages that epidemic routing put out. So as we expected, epidemic routing had a lot of messages in the network. When it comes to individual routing is actually at 0. We don't need to put out additional messages for a node to deliver its own messages because it's only in charge of delivering its own message. So that one stayed flatlined the whole time. When you look at the 3 versions of the LESC protocol, here's a little bit different. If you remember that I told you at the end of our first simulations for message delivery, diversity nomadicity delivered better. But what this is showing us here in this particular case, that interest group co-location helps to keep the number of messages in the system down. And that kind of makes sense, right? If I only designate you to pass messages for me because you're around people that are interested in my message, then if I'm projecting right that you're going to be around people that are interested in it, I'm going to put less messages out there, right? Because I don't need to put a lot out to deliver to if you're around people that are interested in my message, right? Does that make sense? I feel like I kind of rambled there, but yes. So then, and then being a nomad actually delivered more. So coming in, taking advantage of both protocols, the 60/40 case kind of came somewhere, not necessarily in the middle, but it did a little bit better than the worst case between the 3. Now looking at the first message, of course, epidemic routing put out the most messages in the network. In order to achieve that message delivery, we had to put a ton of messages out there to try to get that out to the other nodes. As you see, you see some symmetry between the first message and all message case here, right? You see that interest group co-location performed by putting less messages out in the network, diversity nomadicity, put more messages out in the network, and then the 60/40 case kind of came somewhere in the middle. So let's look at the average number of hops for the messages. This red was supposed to pop up afterwards, but it's okay. Oh, then my battery's gonna die. So in this case, here, that for the average number of hops, as you imagine, since it's epidemic routing is going to hop through more people. You put more messages out. You're basically asking almost everybody you come around to pass a message for you, meaning that your message is going to hop through more people. So epidemic routing, of course, has the most hops in the case of a typical social network. And then you also see that for the LESC protocol, the 60/40 case actually taking advantage of both information for interest group co-location, 60% and 40% of diversity and nomadicity, that we're able to actually get less messages or use less hops than the other messages. And at the end of that was 23%. Now looking at the first message case, we see that of course, the individual messages for both cases is only one, right? I'm only delivering my own message is only one hop. For the other cases, you see the epidemic routing still have more hops than the other ones. And the 60/40 case of LESC was able to take advantage of how the yellow interest group co-location, the hops and how they deliver messages. So let's look at the average energy consumed. And this is, all of them use the same wireless technology, right? They all use Bluetooth Smart. So let's see how they consume energy with putting all this stuff out, sending all these messages. So this is only for the all messages case. The way the simulation was set up, we weren't able to calculate how much energy was consumed by the nodes for the first message case, because it was the first message. It was looking at the first message of the whole simulation, not doing the first message only created by the nodes. So looking at this case for the energy, we see, as you would assume, epidemic routing, you're advertising more messages, you're connecting the most, you consume the most energy by the end. And you see this is in microjoules. They consume the most energy at the end, and as you would also infer that for individual routing, consume the least amount of energy. Only delivered 30% of messages at the end. That means that it used a lot less connections. It advertised probably about the same, but it didn't need to establish connections to only deliver 30% of messages. And then the LESC protocols, all three of them kind of performed around the same. So summary of the results. So looking for at the all message case, for the LESC protocol, this is looking at the 60/40 case, we're able to deliver 4% more messages. So orange is good, blue means worse. So we're able to deliver 4% more messages with 13 minutes less delay. This is the end of the simulation, by propagating 77% less messages than epidemic routing, resulting in 11% less energy used by all of the nodes. For the first message case, LESC delivers 6% less messages at the end of the simulation, but also remember that epidemic routing delivered a lot more messages very fast. It was at 90% very early. But it delivered 6% less messages with 30 minutes more delay by propagating 78% less messages. So it did some things better, but at the end, if you're looking at an emergency message, or you only need to deliver one message to the system, resorting to techniques like epidemic routing can be useful. And then we also designed a simulator to simulate all this that can use Bluetooth Smart, can take advantage of realistic paths. So next, I'm going to go into, and this is perfect, I think I have 7 minutes to go into the application of this. So currently what I'm working on is an application called Alley-oop, which stands for a lightweight, low energy system for ad hoc social message passing, right? We created the name after Alley-oop. It wasn't created before. I'm just a basketball guy. So, so this app, what we intend is developed for iOS applications. How many of you all have an iPhone? So we have, oh, this is great. There's a little bit over half the room. And typically there's like 30 students in here, right? Okay, so hopefully they have more iPhones also. because this should be available at the beginning of April. Putting a lot of work in it now. You kind of seen some of the screenshots of the app kind of transition through over here. Basically, this app will be set up like Twitter. Almost. It'll have the similar capabilities as Twitter, not full functionality as Twitter, but you'll be able to follow, unfollow messages, post messages. You can discover people nearby. And what I mean with discovering people nearby, remember the biggest thing of this DTN is being able to utilize friends that you encounter, right? So if you walk up to somebody and you want to basically follow them, you can see a screen on your list that says just follow this person that's near you if you want to follow that person. To inspire use for trying to gamify it. So the app's called Alley-oop. We're trying to take advantage of some of this techniques in sports and fantasy sports. So basically, even though since we're measuring who you've been around, who you're going to be around, we're essentially measuring how social you are, right? And we're not talking about being social like Facebook by just posting a lot. We're talking about how many people do you physically encounter, right? Or are you typically around? And we're saying that we can use that to say, hey, I'm more social than you as my friend, right? So if I see that some of my other friends are being more social than I am, they're encountering more people, they're passing more messages for people, then try to turn that concept into a competition and make people want to be more social, right? So hopefully there's a good aspect by getting people to interact more with in that case, and hopefully we can get some research results so I can graduate. So, we're trying to accomplish two things there. I think the second one is more important, but that's how we're attempting to get people to use the app. The app currently is set up for people to be able to log in, create accounts using Twitter or Facebook, so you don't have to store passwords and stuff on the app if you don't want to. Or we're also enabling capability to be able to post to Facebook and Twitter. A lot of times, especially there's so many different social networks out there nowadays, it's kind of hard to get somebody to use your social network if it's not integrated with another one. So in our case, we're saying, hey, if you're going to use the app, you can do this gamifying aspect and you can still continue to post to Facebook and Twitter. Acknowledgements. So Dr. McNair, she's my advisor. I started here in 2010. So she's been my advisor the whole time, so I want to thank her. Of course, the WAMS lab. You guys might not know some of these people, but you know Alan's in the lab. He's done some of the work that I mentioned earlier with me on some of the results. And then my committee members for my dissertation, acknowledge them, of course, because I need them to sign the paper. I acknowledge them for their assistance also. And then the ACES lab, I work closely with the ACES lab at the beginning of my research with a former student here in Dr. Figueredo. And then also my funding sources, of course, because they pay for me to be here. So with that, I think we have a few minutes. Before we go into questions, if you guys, so I'm not sure if Dr. McNair told you, but if you guys are able to assist me with using the application, then you're able to get extra credit for the course. So if you help me, I'll help you, right? So if you, and by doing this, over half of you already had iOS devices. Even if you don't have an iOS device, when Dr. McNair announces that the app is released, what you can do is, I think all the libraries on campus have iPads. They have iPad 3s and above, which the application should work in. So if you go you can check out an iPad for free for 1 week. Then you can return it and recheck it out. So if you don't have an iOS device, you can go to the library, check one out, and then participate and still get the extra credit. All right, sound like a good deal? So how many people so far, before we go into questions, would be interested in using the app, testing things of that nature? Okay, so I'm gonna hold you guys accountable. So the first thing I ask you to do is, if you go to this link here, it's kind of different from Dr. McNair's lab website. It's wamresearch.ece.ufl.edu. If you go to that link and you go to the bottom of the page, it talks about the research that I've been working on. But if you go to the bottom, it says, please fill out this survey for mobile ad-hoc social networks. It's a quick survey. I think it'll take max 10 minutes. Ask you questions really quickly about how to use a social network. Do you use Facebook, Twitter, things of that nature? Fill out that survey first. So to get the extra credit, fill out the survey. And then what happens is Dr. McNair is going to announce the app. So if you do the survey and you use the app for the week, and we're going to have things about if you post this many messages, then it'll work. How many of you guys have Facebook? How about how many of y'all have Twitter? Twitter, and then what about like Snapchat, Instagram? Few. Okay, so you guys are basically social already. A lot of people, mostly everybody uses the app. Like I said, Facebook and Twitter you'll be able to post to if you use it. So with that, please visit the survey. Like I said, it's real quick. You can do it for your mobile device as a Google form. So it's real simple. Please visit the survey, and then I'll let you guys ask any questions. What does that? Does that mean I have 5 minutes left or something? 0 minutes left? Okay, I have 0 minutes left. So if you guys want, you can ask me questions after class. Thank you.